Okay, so this is the physics test review. I'm just going to go through a quiz, actually. It's chapter 16 through 18. We'll go through these relatively quickly, but it says, how much force is there between two electrons at a distance of 5 micrometers? Now, whenever we talk about the force between two items that have a charge, the charge force, or the force due to the fact that there's charges, is from Coulomb's law, which says F equals K Q1 Q2 over R squared, where K, so here we're looking for force, K is going to always be 8.988 E9. There's our K. Now Q is the charge of the particle. Because these are both electrons, they have the same charge. Turns out they are both negative 1.602 E negative 19 coulombs. Now, it's the same thing twice, so you could just write squared. That's totally acceptable. I'm just going to write them out. If they aren't protons or electrons, the charge has to be stated explicitly. So you'll either get a certain number of coulombs, or you'll be told what kind of particle it is, whether it's a proton or an electron. And then the last thing is the distance, or the radius, which is we'll just go with 5. It was micrometers, which is E negative 6, but that needs to be squared. I'm just going to grab my own calculator that I have here in my hand and just run this 8.988 E9 times 1.602 E negative 19 times that 1.602 E negative 19. And I'm going to divide that by parentheses 5 E negative 6, close parentheses, squared. It's really important you're able to get that typed in correctly. You should come up with a force of roughly 9.2 or 9.23, depending on how you want to handle that. The 5 micrometers actually looks like 1 sig fig, but regardless of how many sig figs you choose to use, 9.2 E negative 18 newtons should be our answer. There's answer. Question number 1, Coulomb's law. Question number 2 asks that if it says, what electric potential difference? Now when you talk about electric potential difference, that means voltage. So first thing you need to understand, electric potential difference, or electric potential, is going to be used to represent voltage. I could also just ask for the voltage. It depends on that. When we're required to set up an electric field, or an 1800 Newton per Coulomb electric field. So you have to understand electric fields are either measured in newtons per coulomb or volts per meter, but it's 1800 newtons per coulomb. And then we want to figure out, or we said the distance between the plates, these two plates, is going to be 3 centimeters. As we look at the relationship between the electric field, a distance, and a voltage, there's a formula that says the electric field strength is equal to the voltage divided by the distance between the two voltage points. Well, I want to create a V, so this is going to be E times D. So this is going to be 1800 times my distance. If I multiply that D over, the distance is 0.03 to make it into the meters. That turns out to be a straight 54 volts. Okay, so we need a 54 volt voltage source in order to create that from a 3 centimeter gap. Question number 3, what's the capacitance? So right away, I'm looking for capacitance of two plates that have a potential difference. Potential difference, again, it's our voltage of 3.8 volts. And if each of the plates holds 1.4 microcoulombs of charge. Now charge is always a Q, right? Q is our charge. This is 1.4 E negative 6 coulombs, because it was microcoulombs. Well, there's a relationship. Q equals CV is very straightforward. The only variation is that if you had to deal with just finding capacitance without Q and V, you'd have to do it by the formula K epsilon naught A over D, which we did in the homework quite a bit. K is on page 483, epsilon naught is a constant, A is the area, and D is the distance between the plates. So if I don't give you everything for Q and V, expect to use that other formula. But here, it is really straightforward. So Q equals CV. So C would equal my voltage of 3.8 divided by 1.4 E negative 6. Which again, I'm just going to grab my own calculator and throw those numbers in. 3.8 divided by 1.4 E negative 6. Oops, did I do that wrong? Oh, I got that backwards. Dang it. Switch these. I knew something was wrong as soon as I saw it. Capacitances should never be very big. So I have these backwards because I'm supposed to do Q over V instead of V over Q. So those are backwards. So I'm going to fix that real quick and get 3.68 E negative 7. And capacitors are always measured in farads, capital F. Okay. So, yeah, obviously I screwed this up. I was supposed to have Q over V and I had it reversed. So the reason I had to fix that was Q over V, not V over Q, because that was V and this was coulombs. So I had to flip those. Okay. All right. Nothing wrong with making a mistake as long as you know to catch it. If you get a capacitance that's over 2 or 3, you should know there's a problem. If you get a voltage that's like 0.0 or it's like 0.00042 volts, that's probably a concern, unless it's something where the problem is set up to be a very small voltage. All right, question number 4, it talks about, this is really important, electric energy that is stored. Now, stored energy we should always think of as potential energy because it's there for later. Now, we learned about how potential energy can be stored on a capacitor because that voltage gap between them is that electric field. So there is a formula for PEC, which is what we're looking for. So potential energy stored on a capacitor. It has a capacitance of 3.5 microfarads. See, E negative 6 on that makes sense. So our farads should always be small. And a voltage of 6 volts. So if I'm looking at this, my formula for potential energy from a capacitor is 1/2 QV. But I don't have Q. Well, I do know that Q equals CV. So in this problem, I could put 6 times 3.5 E negative 6. That would be my Q. And then this information could come up here. And then I would times it by V again. So really this is going to be 1/2 my Q, which was 3.5 E negative 6 times 6. That's Q, right? This guy right here is Q. I need to times it by V, which is also 6. So we had like 3 versions of this equation. This one would be an example of 1/2 CV squared. The original is 1/2 QV. There's some other ways we can write it as well. But if I do this one, 0.5 times 3.5 E negative 6 times 36, because 6 times 6 is 36, I get 6.3 E negative 5. And because it's energy all year has been measured in joules. Okay, so it's a very small amount of energy that's stored on there. But capacitors are used to release their energy very rapidly. Okay, the last couple of questions. 5, if I'm totally honest with you, 5's not actually going to be on the test. Don't tell anybody, but talks about the peak voltage in the AC wall outlet, which would be V naught. I have VRMS. The average, we're told, is 120 volts. And the formula is that VRMS is equal to V naught over root 2. So if I times by root 2, 120 times root 2 should equal V naught. The V naught turns out to be equal to square root of 2 times 120 is 169.7, so we'll say roughly 170 volts. So that is what's typically in your wall outlets, is 170 volts would be the peak voltage there. And then question 6 and question 7. Question number 6 says, what amount of resistance would be required to set up a 3 milliamp current, given that you only have a 45 volt or 4.5 volt battery? This is a V equals 4.5, I equals 3e negative 3 amps. This is volts. And I know that V equals IR. So if I divide by I, if I take 4.5, divide it by 3e negative 3, I should get R, and R comes out to 1,500 ohms. Okay. I'll ask question number 7. So there's Ohm's law, and then question number 7. Okay. Says how much resistance does a light bulb, a 100-watt light bulb? So when we talk about 100 watts, we're talking about its power consumption. Okay. So power is measured in watts, and it has to operate at a voltage of 110 volts. And we're being asked to find R. Well, to be honest, power is typically related as P equals IV. Now technically, we also know that V equals IR from the last problem. You could combine them into one equation that only uses P, V, and R, but I have zero problem finding the current and then doing it. So here I'm going to say that I would equal P over V, which is 100 over 110. And so if I do that, 100 divided by 110, I get 0.909090, and so on. 0.9090, repeating. And so with that in mind, I come over here and say that 110 volts equals 0.9090 ... R. And if I divide that off, the 110 divided by that previous answer is 121. So the resistance would have to be 121 ohms. And there you are. Hopefully that's enough to answer the questions you didn't get answered on your own. I'll see you in class.